As you know, a log is an inverse of an exponential function. So when we say inverse, we mean this: f inverse x equals y if and only if the function at y is equal to x. Here's our inverse log function. Log to the base a of x equals y if and only if a to the y equals x. That's how we defined it. What are the restrictions on that base? The base has to be bigger than 0 and not equal to 1. Okay, so just a reminder to get your head back in the game here. When I say the log of 0.001 is -3, that's because the base here, when it's not written, is 10. 10 to the -3 is 0.001. If I say log to the base 2 of 32 is 5, that's because 2 to the power of 5 is 32. Okay, we all remember how to change from log form to exponent form. Okay, remember your log laws. Oh, since logs are inverses of exponential functions, then this is true. If I take an exponential function and operate the inverse on it, I'm going to get x. If I take a log function and operate the exponential on it, I'm going to get x. I think this one is easy to see. Let's do a quick little proof for both of them. So log to the base a of a to the power of x. Our power law tells us the x can come down in front. I'm going to get x times log to the base a of a, which is asking you, to what power do you raise a in order to get a? 1. So you're just going to be left with x, which is why log to the base a of a to the x is equal to x. Check. How about this other one? When I take a and I raise it to the power of log to the base a of x, how come I also get x there? Here's how we do the proof. We say this: let's imagine a number y. We're going to call that number log to the base a of x. If y is equal to log to the base a of x, then this has to be true. A to the power of y has to equal x. Okay, so then let's start from the beginning. I've got a to the power of log to the base a of x. Then instead of writing log to the base a of x, I'm going to write y. So I've got a to the power of y. Well, what is a to the power of y? What is a to the power of y? It's just x. So log to the base a of x is the same as a to the y, but a to the y is just x. So I think we did this proof by number examples last year, and I think we did it this way. If I said 10 log to the base 10 of, let's say, 5, and I said, what's, oh, I made it easier. And I put, let's say, 100 in here, and I asked you to solve it for me. What is 10 raised to the power of log 100? And what's the answer to that? Well, we have to go about this from the inside out, as in start by answering this question: what's log of 100? To what power do I raise 10 in order to get 100? It's 2. Now, raise 10 to that power, what do you get? 100. Okay, so you're operating a function on its inverse. Whatever you put in is what you get out. Okay, log laws, remember them? When you're multiplying inside, you add outside. When you're dividing inside, you subtract outside. When you have a power, you can bring that exponent down in front. Okay, so how do we simplify these? Well, the bases are the same in your subtracting. Law 2. Change that into a division. This becomes log to the base 2 of 80 over 5. What is 80 divided by 5? Log to the base 2, I guess it would go into there, what, 16 times? Which is just asking you, to what power do you raise 2 in order to get 16? 4. Okay, would you please do the next question? Remember, when the base isn't written, assume it's 10. Are you guys all getting 2? Okay, and this one, the bases are the same and we're adding, so we've got log to the base 3 of 6 times 1.5, which would be log to the base 3 of 9, which would be 2. Okay, natural logs. The logarithm with a base of e is called the natural log. It means you've got log to the base e of x, and because it comes up so often, we give it a name. We call this ln x. So you pronounce it just like go mow the lawn, but you write it ln x. Okay, so that's how it's pronounced. And this is what it means. If the ln of x equals y, then e to the y is x, which tells you that the ln of e to the x is x, and e to the power of ln x is x. Okay. Can you find x if the ln of x is equal to 5? Well, look back at the definition. Ln x equals y means e to the y equals x. Ln x equals 5 means e to the 5 equals x. This is an exact answer. Can you tell me to 2 decimal places what the answer is? 148.41. Okay. And remember that although that looks so nice and accurate, it's approximate. You're rounding off. Okay, let's look at solving some equations, only now we're going to be working with the base of e, which you will for most of this year. So solve the equation e to the power of 5 minus 3x equals 10. We're looking to solve for a variable in the exponent. We want to take the log of both sides. When the base is e, we're going to take the ln of both sides. Okay, so I've done the same thing to both sides of the equation. I've taken the ln. And then I'm going to use my power law and bring the exponent down. That is 5 minus 3x times the ln of e is equal to the ln of 10. Okay, what's the ln of e? Well, this is just going to equal 1. So I have 5 minus 3x is equal to ln 10. Solve that for x, subtract 5 from both sides, and I get negative 3x equals ln 10 minus 5. And finish this up, I get x equals ln 10 minus 5 over negative 3. Or I guess we could have written it this way, 5 minus ln 10 over 3. Pull out your calculators and convince yourself that those are both the same thing and that you know how to move a negative sign from a numerator to a denominator or vice versa. Write this as a single logarithm. Our bases are the same. Remember the rules for combining logs. Your bases had to be the same and you had to get rid of those coefficients before you started. So this is ln A plus ln B to the 1/2. So bring the exponent up first. The bases are the same, they're both lns. We're adding outside, which means we multiply inside. The ln of a times b to the 1/2. You could also write it this way, the ln of a root b. Both of these are acceptable. One is just in exponential, the other in radical notation. A really important formula for changing bases. How do I change the base? For a log to the base a of x means you've got log of x over log of a, or in this case, ln x over ln a. I'm not going to do the proof right now. If we have time, we'll do that tomorrow. But I'd like you to evaluate log to the base 8 of 5 using this rule. So log to the base 8 of 5 is asking you to what power do I raise 8 in order to get 5? Well, my rule says this is just the ln of 5 over the ln of 8. So plug that in your calculator. Last year you would have done this. Convince yourself that you're getting the exact same answer. And we're going to try to find the inverse of the formula. The formula we had was this. The mass at any time t, and this was for this isotope with radioactive decay, was the initial amount times 1/2 to the little t over 25, the length of the half-life. Look at this formula and tell me why they're the same thing. Why are those two formulas considered identical? Because a negative exponent would be take the reciprocal of the base, which would make it 1/2. In some fields of study, when you have decay, you will see a negative exponent, but the base will always be a a number bigger than 1. And in other fields of study, when you have decay, you'll always see a fraction in the exponent. So make sure that these sorts of things don't confuse you. They're the same thing. So how do we find the inverse of a function? Well, let's try taking this function, mass remaining is equal to 24 times 2 to the power of negative t over 25, and let's find the inverse, aka exchange m and t and solve for m. That is, t is equal to 24 times 2 to the negative m over 25. So what are we doing here? We are finding the inverse. So we start off by isolating our exponential. T over 24 is equal to 2 to the power of negative m over 25. Solving for a variable in an exponent, we're now going to take the ln of both sides. A ln is a log. So ln laws, log laws, same thing. I've got the ln of t over 24 is equal to negative m over 25 times the ln of 2. Solve this for m. I multiply both sides by 25. And let's divide both sides by negative ln 2. So I've got 25 times the ln of t over 24 divided by negative ln 2 is equal to m. So that's the inverse. So we would say not m is equal to this, but now m inverse of t is equal to, we'd say t at this mass is negative 25 times the ln of m minus the ln of 24 all over the ln of 2. So when will the mass be reduced to 5 milligrams? Now you're just putting 5 in for m. And if you plug that all in your calculators when you get home, you should be getting 56.58 years. And then I'm going to let you practice graphing a ln function. By the way, a ln function inverse of e to the x looks like this. And from there, it's just transformations. For your homework, would you do all the homework questions except for the ones that refer to inverse trig? We'll start it again. Okay, so keep those things in mind, and just a little bit about notation. So you know how this notation, sine to the minus 1, the inverse notation for a function, can get confused with the reciprocal notation, 1 over sine, which is cosecant. To keep us from doing that kind of confusion, you will also see this as your notation. Sine inverse x might be written, and in your textbook it is, as arc sine x. So it's nothing new that you didn't already know. It's just a word you haven't used before. And arc cos and arc tan mean correspondingly the same things. Okay, so our sine graph, we have it graphed there on the back board. It's not one-to-one, is it? It's a function, but it's not a one-to-one function. It doesn't pass a horizontal line test. So that odd function back there is failing our horizontal line test, which is why you would get how many solutions if you did a sine inverse. Well, your graph would look like that. So picture that sine graph tipped on its side. It's going to look like that. That's not a function. So what we do is we restrict the domain. Okay, so a quick sketch of your sine graph right here. Center top, center bottom, back to the center. And I'm actually going to do 2 rotations. That is from negative 2 pi to positive 2 pi. And pi by 2 and negative pi by 2. Okay, so this sine graph, in order to keep it one-to-one, we just look at a little part of it. So part of it that's going to give us the entire range from negative 1 to positive 1. And we want the entire range out of it, but we want to restrict the domain. So it gets restricted from negative pi by 2 to positive pi by 2. So in Math 12, I told you when you want a reference angle, remember if it wasn't one of the special ones and we had to inverse sine it on our calculator, I said your reference angle always positive, and then we reinterpreted it back in terms of our bow tie that we had drawn. If you're just using your graphing calculator, you can get a negative answer. Then it's complicated because you have to remember that that is referring to something in the 4th quadrant where your sine is negative. So it's really giving you answers in the 1st and 4th quadrant when you use the inverse sine button on your calculator. And from there you have to interpret what the reference angle is and figure out what it is you want. Okay? So domain restrictions on sine inverse, you need to know what they are. Negative pi by 2 to positive pi by 2. And of course, the range, so in order for us to say sine inverse x equals y, it means the sine of y is equal to x, and we restricted the x between negative pi by 2 and positive pi by 2. So our domain for sine is all reals, which we just restricted. And our range was from negative 1 to positive 1. When we take the inverse, our domain will be from negative 1 to positive 1, and our range will be from negative pi by 2 to positive pi by 2. So for sine inverse, then the number you put in has to be between negative 1 and 1, and the number you get out will be an angle in either the first or the fourth quadrant. And then you're going to have to interpret that answer in context. Okay. Let me ask you a question. What is sine inverse of the sine of 30 degrees? Say it out loud. 30 degrees. Okay, what is the sine of the sine inverse of a half? What is it? 1/2. Okay, well, here's a trick question. What is sine of sine inverse of 30? If you don't know the answer, put it in your calculator. Is it working for you? No, you're getting an error. Okay, how come? Because it's not in the domain of the inverse function. Okay? So don't just sloppy look at this and say the answer is 30. This does not exist. Why not? Because we tried to put something that is not in the domain of our composite function. We've got a composition here. Composition works from the inside out. And if you break the inside function, you're never going to get here to the outside function.